We're going to have a look at how you determine whether something shows optical isomerism, and then if it does, how you would actually draw the enantiomers. First thing to do is to determine whether your carbon in your molecule is actually asymmetric or chiral. There are 2 points that you would have a look at to determine whether the carbon was asymmetric. The first thing is the carbon needs to be tetrahedral around it. So you're looking for a situation where you've got the bond angle approximately 109.5. If it's square planar, for example, in a carbonyl and a ketone or an aldehyde, then it can't be chiral. So you are looking for a tetrahedral carbon. Once you've identified that you have a tetrahedral carbon, you need to check the molecule to make sure it has 4 different functional groups. If you've got a large molecule or a complex molecule, you'll have to sort of go around the molecule on the carbon chain and prove that each side of your chiral carbon has a different set of functional groups. If your answer is yes, that it is a tetrahedral carbon and that it has 4 different functional groups, then it has an asymmetric carbon or a chiral center, and we show this with an asterisk. How to draw the enantiomers out. So you would get 2 enantiomers if you've got a chiral center. So the first thing is you need to draw it as a 3D diagram. So to do this, you'd use a Fisher projection. So the simplest way of doing this, to learn how to do it, is to draw 2 in plane. That means 2 solid lines. 1 coming out, which is the wedge, and 1 going behind the plane, which is the dotted line. So you can start drawing the enantiomers by showing 2 single lines, a wedge and a dotted line. So this little diagram just shows you what it means by the different Fisher projections. So you've got 2 in plane, 1 in front and 1 behind. Once you've done that, you need to draw the mirror image of this Fisher projection, so you have the 2 enantiomers outlined to start with. So here's 2 carbons ready to put on the 4 different functional groups. Then you'll need to add your 4 different functional groups. It doesn't matter where you put either the Fisher projection lines or the functional group, providing you end up with a mirror image at the end. So you can see I put the 2 in plane with the hydrogen hydroxide. I put the wedge coming out with the CH3 methyl group and the dotted line with the CN group. As long as you've got the mirror image, as you can see, the dotted line has the CN on both, the plane line has the hydrogen hydroxide on both, etc. So you add it in, so you've got 2 lots of enantiomers showing 3D. As I say, it doesn't matter where the groups are as long as you show them. Once you've got your 2 mirror images, if you then have 100% of one isomer, it can be distinguished from the other by physical methods only, so you'll need plane polarized light. So if 100% of one isomer will rotate plane polarized light an equal but opposite way to 100% of the other isomer. It's impossible to tell which way it's going to rotate the plane polarized light by just looking at your 3D diagrams. Each isomer on these 3D diagrams will be called an enantiomer. If you have 50% of one enantiomer and 50% of the other enantiomer, we call it a racemic mixture. This equimolar mixture will have no effect on plane polarized light. Let's have a look at another example where there's an asymmetric carbon. If you look at 2-hydroxypropanoic acid, you look at the main structure, you can see that the middle carbon has a chiral center. So just to check, it's tetrahedral around that carbon and it has 4 different functional groups. In this case, it's got a hydrogen, a COOH, an OH and a CH3. Once you've established that the carbon in the center is chiral, you need to draw your Fisher projections for both your enantiomers. So put 2 lines in plane, 1 wedge to show it coming out, 1 dotted line to show it going behind. Again, it doesn't matter where you put your functional groups as long as your mirror image shows them in the same places. These isomers or enantiomers are now non-superimposable isomers as shown.